Hello, this tutorial will introduce how can we use R to build a decision tree model for making classification decisions. So this time we will use the R Markdown to introduce the R commands. And we are going to use the income.csv file, this income dataset, to build this decision tree model. So basically we have 12 different variables and we have 3 numeric variables and the rest of them are categorical variables, are factor variables. And we have one income variable, which is our classification target variables. So basically we want to use these 12 variables to build the decision trees, and we want to use the decision tree model for future prediction of this income. So let's get started. First of all, we should set the working directory and import the data. So let's import the data. And next, we usually getting the structure and the summary of the data after we import. So let's see the structure of the data. So in total, we have 12 variables. We can see that 3 of them are numeric variables and the rest of them are factors. Well, one thing I want to mention here is when you import this income.csv file, because the how many, like 12 minus 3 equals 9, so the 9 character type variables are all factors, are all nominal variables. So we here set this string says factor equals true. So we want R to convert those character variables to factors directly when we import the data. And let's see the summary of this data set. So basically it will show you the frequency of different levels of for the factor variables and all the sample statistic results for the numeric variables. Well, next we want to see how many rows inside this dataset, so we'll use nrow function, and let's see. So in total we have almost 32,000 data in rows. And next we want to see like the distribution of this income variable. So we want to see how many people are have income larger than 50K and how many are less than 50K. So let's use this table function. So almost 25,000 people had income less than 50K, and 7,841 people had income larger than 50K. And we want to see the probability instead of frequency. We want to see the probability of this distribution. So yeah, almost 76% of people have lower income. Well, next, we want further explore the data, so we will show you some basic simple data exploration of both numeric variables and categorical variables, factors, as well as the target variable. So let's first build the histogram for all the numeric features. So in total, we have 3 numeric features. So this is the histogram for the age variable, and we can also build the education years and also the working hours per week. Well, remember you can always change some parameter inside this histogram function. For example, if I add a new parameter called breaks equals to 5, now I only have 5 different columns. So basically they separate the age equally into 5 divisions. And you can also use another parameter called frequency. So we put frequency equals to false. So the y-axis will no longer be frequency. Instead, it will be the density. Well, next we will show you how can we create a dummy variable. Well, we want to create a new numeric column, and the value of this column is the recorded value of the income variable. So for example, if the income is larger than 50K, we want to give the new variable a 1, value 1. And if the income is less than 50K, we want to give the value 0. So there are two approaches to do it, and there are a lot of more we didn't present it here, but you certainly can find it somewhere else. So the first approach is if-else function. So if this income variable, the value of this income variable inside this data set has equals to larger than 50K, we will give the value 1 to this income high, this new numeric variable. Well, if it is not equals to this larger than 50K, it will give a 0 to this income high. Well, similarly, you can use this bracket. So you put this condition inside this bracket. So if the value of income variable equals to less or equal to 50K, and you will give a value 0 to this new numeric variable income high. And similarly, if it is larger than 50K, we'll give a value 1 to this new variable income high. Well, the reason we use this numeric variable, we create a numeric variable, is we want to use this numeric variable to see the correlations with other numeric variables. Well, next, let us run this line of argument. Basically, this line of argument and these two lines of arguments serve the same purpose. And let's check the structure of this data set again. So now you can see that beside this income variable, we create another numeric variable, income high, and it has two values, 0 and 1. And we will use this numeric variable to generate the correlation matrix with other numeric variables. So we have another 3 numeric variables. So in total, we have 4 variables. And we will put these 4 numeric variables inside this vector. And it will output a correlation matrix for these 4 variables. So let's go ahead and run this chunk. So the closer to 1 means they have a strong correlations. But here, while they're positive, so they have positive correlations. But they're not close to 1, so I don't see any strong correlations here. Well, you can also visualize the correlations using a scatter plot, but using the function pairs. But it will take a long time to load, so you can certainly try them out offline, so I will not present it here. Next, we want also to retrieve the relations between 2 factor variables. For example, we want to see the relations between the income and the work class, and the income with the occupation and so on. So we'll create a table, include these 2 variables inside this table. So let's see. The income and the work class. So it will generate the frequency for both level of income and each level of the work class. Well, you can do this for each factor variables. So we can know that the farming fishing, the people with farming fishing occupation has 879 people has less than 50K income. And another thing, you can also use the prop table. Well, I want to introduce another features here inside this prop table function. So you can put a margin parameter here. So if the margin parameter equals to 1, the margin index equals to 1, the prop table will output the probabilities, and the sum of each row of the probability equals to 1. Well, if you change the margin index equals to 2, let's run this one too. Well, the sum of the probability for each column will equals to 1 now. So you can see, well, if I have a professional school graduation, I have that degree. Well, I will have 73, almost 74% to get an income larger than 50K. Well, if I only have a preschool degree, oh, there is 100% I will have an income less or equal to 50K. Well, if you have any questions about any functions, remember to use the help option. So remember to put a question mark, to type a question mark. Well, next, we no longer need this newly created numerator variable income high. So we want to remove this variable from our data set. Well, there are two approaches we present here. And the first one is you can put a non-value to this variable. And next, we will use the minus sign inside in front of the index and copy this data income data frame back to the original data frame. So let's try. So basically, these two lines of our command are equivalent. So let's check our structure of dataset again. So see, we no longer have the income high variable. Well, before we build a decision tree model or any other classification models, well, we need to partition our dataset into training and testing datasets. Sometimes we also need a validation dataset. Well, here we only partition them into training and testing. Well, we need to first load the library caret to, because caret is a library include the functions of data partition. So let me first load this one. It will take a few seconds to load this library. Well, the next one is we need to set a seed. Well, in order to get a reproducible random result every time, we need to use this seed. And the number inside the seed function is, well, it's a random number. Well, you can give any numbers, but for every time you change a number, you will get a different random result. But if you keep this number consistent, every time you randomly generate results, you will have the same random result. So let's set the seed equals to 100. Well, next we will use this create data partition function from this library to generate a sequence of row index. So here we see p equals to 0.5 means we want 50% of the rows from the original dataset and to include them into the in-train variable. Let's see the top 10 values from this in-train variable. So you can see it basically is a column of index randomly generated. So we want those rows with this randomly generated index to put those rows into the train data, and the rest of the rows, the rest of 50% of the rows from the original data set, to put them into the text and test data. Well, next, further, we want to partition the text data into text 1 and text 2. we also use this create data partition function. And see here, we also p equals to 0.5 means, well, we want to separate this text data equally into two data sets, randomly select. With those index, we put them into text data 1. Without those index, we put them into text data 2. Well, next, let's check the rows for the training and testing data. Well, first, let's see the rows from the original data set. So the training data set should have like half of the rows, so it has half of the rows. While the test data 2 and text data 1 should have the same row number. And they're all like half of the row number from the trained data set. Well, because we randomly generate those training and testing data set, well, the distribution of the target variable income should be the same. So let's check. So this is from trained data set. This is from the test 1, and this is text 2. So basically, they all has almost the same distribution, the proportion for the target variable income. Well, now we have our training dataset and testing datasets ready. Well, next we want to build a new decision tree model based on this training dataset. Well, the first thing we need to do is to load this library. So let me load this C50 library in order to build a C5.0 decision tree. And next, we will use this C5.0 function to build this decision tree based on the training dataset. The first parameter is the training data frame without the target variable. So we need to exclude this income variable. So we use this -12 to exclude this income variable. While the next parameter is the target variable from the training dataset. So let's run this model. It will take a few seconds. And then let's print this decision tree and see some summaries. Well, you can see it is a very complex tree. So let's find a single path and walk through that path. So here's one. Well, if you have the value of the relationship is from these 4 levels, and the value for the education variable is from these levels, you will have the income less or equal to 50K. Well, the values inside this parentheses. So this 8,774 is the examples that reaching this decision, and the 515 is the example that has been incorrectly classified. So you can see it's really complex tree, but well, it has a subtree here, so its subtree starts here. And well, in total we have 2,505 examples being incorrectly classified. And see here is a confusion matrix we have for the training data set. So well, we have these and these numbers are the examples has been correctly classified. Well, the rest of the numbers are the numbers of example that has been incorrectly classified. So this number plus this one equals to this 2,505. So they also show you the attribute usage. So the relationship has been 100% used. Well, after building this decision tree model, we want to see how this model performs on our text data 1 and text data 2. So we'll use this predict function with first parameter is the newly created model. The second parameter is the text data. and we want set the type equals to class. So basically, this predict function uses the C50 model we just created and to use the text data, the 11 features from the text data 1, excluding the target variable income, and to predict the income for the examples that from this text data 1 and text data 2. So those output of this predict function is a column of incomes, like income classes, like less or equals to 50K or larger than 50K. Let's run this first predict function. It will take a few seconds, and then let's see the summary. So about more than 6,000 examples from text data 1 has been classified into less or equal to 50K class. And let's see their performance on the text data 2. We also use the predict function. And also more than 6,000 examples have been classified as less equal to 50K. Well, we want to compare the prediction result with the actual income value. So we select the top 10 rows from the example with the relationship equals to own child and unmarried. So let's see those two comparisons. So basically, if the top 10 rows show us that this is the prediction from using our model. This is their actual value of income. So these 10 rows, these 10 examples has been correctly classified. So is the relationship equals to own child. Their income is also being correctly classified. Well, similarly, we will give another 10 rows to show you the results comparison for the text data 2. So you can see here, those are predictions. This column is the actual value. So these two columns are equal, means we have the correct prediction. Well, next, in order to evaluate the performance of this decision tree model on text data 1 and text data 2, we need to create a confusion matrix and some other metrics in order to see in order to evaluate the performance. So the first function we're going to introduce is confusion matrix. Well, the first parameter inside this function is the prediction generated from this decision tree. And the next one is the actual income values from this text data 1. Well, and we want the positive class equals to larger 50K. And the DNN will present you with a vector. So the first character element is prediction, which is the title for the first element. And the true is for the title for the second element. So it will give a row column and the row title and column title for this confusion matrix. So let's run this one. So you can see, okay, we now have this confusion matrix right here. So about 5,633 instances are actually less than 50K. And they also correctly classify as less than 50K. And these two numbers represent the examples of incorrectly classified examples, the number of those incorrectly classified examples. Well, you can see, well, the accuracy is equals to 0.83. And we can also see here the sensitivity equals to 0.656. Well, sensitivity is equals to recall, and also the specificity and the positive predict value is equals to the precision. So now those are the those are the metrics we have from this confusion matrix. And next, well, you can also use this function to output the performance for the text data too. Well, the next function we want to introduce is the M metric. Well, before you use this M matrix, remember to load the library R minor. Well, it will take a few seconds to load. Now we have successfully loaded this package. Let's use this function. Well, the first variable, the first parameter is the actual value of income, and the second one is the predicted value generated from our decision tree. And we want to output the accuracy, precision, the recall, the true positive read, and the F1 measure. So let's output this one. So it will give you all these parameters in 2 lines. So we can see we have accuracy and we have precision 1, precision 2. How can we distinguish those 1 and 2? Like those 1 and 2 are depending on the class of the income in the first row of this test data 1. So for example, now let's generate the top 5 rows from the text data 1. So you can see, okay, the level of income variable from the first row of this text data 1 is less and equals to 50K. So this precision 1, this true positive read 1 and F measure 1 are corresponding to this less than equal to 50K class. So also, well, let's generate this matrix for text data 2. And you can see, okay, the first element, the first class of income is also less than equals to 50K. So this precision 1, F measure 1, and recall 1 are corresponding to this class, less than equal to 50K class. Well, besides building a decision tree using C 5.0 model, we can also use J48. So we now will introduce another decision tree model called J48. And it is based on C 4.5. And there are minor differences between J48 and C 5.0. Before we build a decision tree, we need to load this library RYCA. So let's load this library. It will take a few seconds. And next, we use the J48 function to build a decision tree based on the training dataset. Well, see the first parameter. It looks like a regression model, but now we use a dot to represent the rest 11 variables, like excluding the target variable. So target variable is right here. So the second parameter is the data. Data equals to the train data. So let's build this model, J48 model. Well, next we will evaluate the performance of this model on the testing dataset. Well, besides, we no longer need those confusion matrix and metric functions anymore. We only need this evaluate VECA classifier function from this RWECA package, and it will output everything we need from confusion matrix to the precision and recalls. So, well, you can see that accuracy is here and the confusion matrix is down here. And we can also have the precision recall, F measure values, and other values included in this output. So basically, this function presents everything we need to know, and it's really comprehensive. Similarly, we can output the evaluation for data test data 2 and see the accuracy and confusion matrix and so on. Well, next we will present you how can we create a decision tree model based on selected variables. For example, we no longer need like all 11 features included in this decision tree model. We only want the 2 variables, relationship and education. Well, instead using this dot, we will create looks like a regression. So we use relationship plus education. While the data is also the training data, we want to build this decision tree model based on the training data set. And then we still use C5.0 function. So let's build this model. And let's look at this model, check the complexity, and compare with the model before. So look, we only use 2 variables, so the tree is much simpler than before. And see, we only have 2 attributes usage here. Well, let's see the performance of this simpler decision tree on the test dataset. So let's first use the test data 1. And then we see the confusion matrix. So you can see that even though it only include two variables instead of 11, the accuracy is still above 80%, and it's not bad. And the sensitive, the recall value has dropped a little bit, but the specificity value has increased. Well, we can also use the test data 2 to see the performance. Well, the accuracy is also about 80%, so it is not bad. Well, remember, you can also use this add metric to see the performance. Well, the F measure is really high, even though we only use 2 variables. Well, besides C5.0, we also want to see like using this select variables to build a J48 decision tree. So we use, just ignore this part first. So we only include relationship and education. Let's see the result. So this is performance on the test data 1. Well, you can see similarly the accuracy is above 80%, and F measure for the class less than equal to 50K is also about 98%. Well, next we will demonstrate how to perform this tree pruning technique in C5.5, C5.0 and J48 decision tree model. While tree pruning is a technique used in machine learning and data mining to reduce the size of the tree by removing some less important sections from the tree, and it will improve accuracy by reduce the overfitting. So in order to perform this tree pruning, we need an additional parameter inside this C5.0 0 function when you're creating this decision tree? Well, the parameter is the control parameter, and you need to set a value to the CF variable. So we first set a CF variable equals to 0.05, and then next we will try 0.5. So let's first try the lower level and see the results. Well, it built a less complex tree compared with the first C5.0 tree we had. And we give the CF a higher value. And see the pruning results. Well, it has a more complex tree than the lower CF value. So in conclusion, so with lower CF value, well, we will have a less complex tree. With higher CF value, we will have a more complex tree. So with lower CF value, we will remove more sections from this tree, while with higher CF value, we will remove less sections from the tree. Well, similarly, we can also pruning the G48 tree by giving this giving the value to the C variable. So it also have a parameter called control, and we first try a lower value to the C and a higher level to higher value to the C. Okay, let's compare these two trees. So, yeah. The one with lower, so you can also see from here, and you can also try yourself offline. With lower C level, well, with lower C value, we will have a less complex tree. With higher C value, we will have a more complex tree. Well, when you finish everything and you're trying to turn in your assignment, don't forget to create an output file by click Need PDF, or you can go Need Word or Need HTML. Everything works. Let's click. Now I have this PDF file created after a while because it generated 71 pages, so it took a long time. Well, basically everything, including your code, your comment, and your outputs, the plots you generated, the decision tree you made, are all included in this file. So yeah, so this is everything we need to cover in this tutorial. Thank you for your time and thank you for listening. Bye.